There we go. I'll begin with a word of prayer. So here we go. Heavenly Father, we thank you for this day. I thank you for these students and our visitors rather, and just pray that you'd bless this class, Lord. Help us to understand a little bit more about Hilbert Spaces and orthogonality today, Lord. In your name I pray, Lord Jesus. Amen. So, let's see here. Oh, so yeah, I just, for the sake of, at some point, I will have some future student in some future year, and I'll be like, how did I solve that problem? So here, this is the idea for like number 9, part A.
I had the exact same idea.
Something like that.
I did have the exact same idea.
Yeah.
We just did the partitioning differently.
Yeah. I'm not saying you can't do it that way, Audric. I just don't know without, like, I had to sit and look at your paper.
Yeah.
Okay, so we're talking about Hilbert space. What's a Hilbert space? A Hilbert space is a complete inner product space, right? So a vector space with an inner product. So that's our context here. So you got like E with inner product, right? And it's complete. And then we define the norm to be induced from the inner product like this, right? Okay. So definition. Come on. Let's see here. Let me read the prelude here. He says, by a basis of a vector space E, we mean a linearly independent family of vectors such that it spans the space, right? We do look at finite linear combinations for the span, all right? But he says in inner product spaces, orthonormal bases are of much greater importance. Oh, instead of finite combinations, infinite sums are allowed, and the condition of linear independence is replaced by orthogonality. One of the immediate advantages of these changes is that all the important examples, it's possible to describe orthonormal bases. And then he starts describing more about that, but let's get into it here. So, well, I'm surprised by that. I didn't. All right, so definition, family S non-zero vectors in inner product space E is called orthogonal system if X is perpendicular to Y for any distinct X comma Y in S. If, in addition, the norm of X is equal to 1 for all X in S, then S is called an orthonormal system. This language system's weird to me, guys. But, you know, maybe there's a reason for it. Will become clear for why he's not just saying set here. All right. He says, okay, so any orthogonal set of non-zero vectors can be normalized, right? So that's easy enough to prove. How do you do that? Let's see here. So like, So I said, so here's a theorem. If S is orthogonal system, then S1, we can define S, like, is that his standard notation maybe? This may be his standard notation. I don't know. S1 is equal to X divided by norm X such that x is an S is, orthonormal system. So this is the usual trick, right? If you want a unit vector, divide by the length. So, yeah. Whoa. He says, if x is orthogonal to each of the each of y1 through yn, then x is orthogonal to every linear combination of vectors. So, it's another theorem. If x is perpendicular to yi for all I equals to 1 to n, then x is perpendicular to cj, yj. So any linear combination of the y's, right? So the proof of that's actually, very elementary. We just do x with the linear combination, right? And that gives us the sum using the conjugate linearity in the second slot, right? The conjugate is cj, x with yj. But this is 0 for all j, right? So you get 0, which then proves that x is perpendicular to any linear combination of the y's. So.
I think I got distracted. Where does the c come from in the second theorem? Is it?
Oh, the c is just arbitrary constants.
Oh, okay.
So like we're just.
I figured it was a constant c, but it was also like. Oh, thank you.
Mm-hmm. Okay, so theorem 3.42, orthogonal systems are linearly independent. All right, so see, he's still only doing things with finite sums at the moment. So this thing he had in the preamble about extending linear combinations to like series, he's not made good on it yet. I guess we're going to get to that, all right? But so the proof just looks like this, right? What does it take to show something linearly independent? So suppose you have, the sum of, let's say, cj, yj equals to 0, j equals 1 to n, where y sub j are an element of this orthogonal system S, right? Right? Then if, let's see here. Interesting. Okay, so then he's like, then if we look at, 0 with this sum, that's 0. But then he then puts the sum. I don't know why he does it in two steps. Like he then puts the sum in the other one as well. So I can change the index I equals 1 to n, of CI, YI. That's 0, right? Right? And then using properties of the inner product, we can pull out the summations. I equals 1 to n, sum j equals 1 to n, and we've got ci, cj conjugate, right? And then inner product of yi with yj.
Is inner product something we learned in linear algebra?
It could be a dot product. It could be a lot of different things.
Okay.
But for us, it's usually an integral over like a pair of functions.
Okay.
But it's basically just like an abstract, a dot product, but in a complex vector space.
Okay.
So, yeah. Now, this if you want an equation that defines orthogonal system, like orthogonality could be rephrased like this: yi, yj is the length of y squared times the Kronecker delta ij. Right? Where the Kronecker delta is what? It's exactly 1 if they're equal, 0 if they're not. And so like what the Kronecker delta will do is it'll squish this sum. It'll basically put I equals to j, so we could keep the sum over I, let's say. And then we've got ci bar, and then the length of yi squared. In other words, that's the inner product of yi with yi equal to 0, yeah? And so that, you notice, is, what is that? We're looking at the sum I equals 1 to n of the modulus of ci squared times the length of yi squared equals to 0. So what is that force? So you've got a sum of positive things, right? Because the length of yi is, we're assuming non-zero vectors. That's where this system has to be non-zero.
So all of the coefficients have to be 0. That's
So this implies that all the coefficients have to be 0. Yeah. Now this is not the proof I usually give in linear algebra at all. You know, like typically I take the inner product of the linear combination with a particular vector, and then I get that the arbitrary coefficient has to be 0. So this is kind of it's a different attack than the one I usually use. So, all right. So that's that. Let's move on here. So next definition. So then that implies linear independence, right? Because we took the trivial combination, we took the linear combination, which was 0, and it forced us to have all of the weights of the combination to be 0. So the next thing here definition. Orthonormal sequence. All right. So a sequence of vectors which constitutes an orthonormal system is an orthonormal sequence.
You're amazing at that. That was your own fault.
Oh, look, Kronecker delta. So he says in applications, it's often convenient to use sequences indexed by the set of all integers z. The condition of orthonormality of a sequence can be expressed in terms of the Kronecker delta, as he says there. All right. So I still feel like I'm not entirely. I'm still a little bit perplexed as to why we're not saying set instead of system here. Like maybe there's other terms and privileges that this word system entitles us to, but it seems like I would prefer to use the word set there, unless, I mean, there is, maybe it's an ordered set, maybe that's it. I don't know. Obviously, if it's a sequence of vectors, then it's an ordered list, right? I mean, you could think of it, you could identify the sequence with its range, essentially, right? The set of vectors which the sequence goes, and that which constitutes, like this is very slippery, not entirely mathematical language here. I don't know, I'm a little miffed with this definite. Anyway, let me go on. So some examples. Some examples. Oh, sorry, Audric.
It's okay.
Oh, I was talking about Audric.
Oh, yeah, Audric and Audrey.
Yeah, our visitor's Audric. What are the odds?
Well, there's two of them, so isn't it even now?
What's that?
I thought you were writing on the other board, so I went to go get coffee while I waited.
Oh, sorry. I moved you over here. I think
Okay.
are you, I think I,
Yeah, that looks good enough.
okay. So, example, let me move along here. Number one, of course, you can do, oh, interesting. So, this is not what I thought it was. En equal to, well, let me say it this way. En J is the sequence Kronecker delta Nj, which is to say that it's 0, 0, dot, 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 until you get to a 1, and then zeros afterwards, right? But it goes on and on. So of course that's the nth spot, nth entry. So these are elements of L2, right? He says this is an orthonormal system in L2. So S equal to E1, E2, dot, 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 gives orthonormal system in L2. Okay, so that is more than I was kind of expecting there, yeah? Number two, he says let phi n of x equal to e to the in x divided by the square root of 2 pi for n an element of the integers. And the full integers, not just the positive ones either, all right? Then he says that this is an orthonormal system in L2. So if you look at S, phi n such that n is in Z gives orthonormal system for L2 minus pi to pi. So the locally integrable functions in there. All right. Can you see that, Audric? Did I need to move you?
Yeah, you're good.
Okay. Okay, so let's work that out right quick. So he's claiming that these are, orthonormal, right? So let me work that out. So we have phi n of x, phi, let's say m. Well, let me not use m and n. Let me use let me use I and J. All right. Oh, I is a bad choice here. Let's try that again. N and, I don't know, P. Oh, thank you. So that would be equal to the integral from minus pi to pi, right? Of phi n of x, phi p of x conjugate dx, which is equal to the integral from minus pi to pi of e to the I n minus p x over 2 pi dx. Where I use the complex conjugate, of course, is gives us the minus IPX, right? And then this gives us 1 over 2 pi I n minus p e to the, I n minus p pi minus e to the minus I n minus p pi. Yeah, good. That's just like you said, that's the sine of n minus p times pi. We used up the 2 and the I to make the n, so we've still got a pi times n minus p there, but of course that's equal to 0. Now we've assumed something here, right? This is for n not equal to p. And then on the other hand, if we look at, the inner product of phi n with phi n, we've got the integral from minus pi to pi of dx over 2 pi, which is equal to 1. Because when you have n equals to p, the conjugate in itself, they cancel out and you just get 1 over 2 pi. So there you go. This is a orthonormal system for L2 minus pi to pi. And it's particularly simple, right? Like this is a very nice set of functions. Like what could be simpler than this, Of course, we can make this look more complicated by expanding in terms of sines and cosines and things, right? But, yeah. The next example is more technical. The next example is Legendre polynomials. So, what?
Oh, gotta move your digital student.
That's right. See, I've got Jacob doing he's moving the camera in the back. I'm moving the zoom in the front. Is that good, Jake? Audric?
Just a little bit more. You went out of frame. Perfect, yeah.
All right, so the Legendre polynomials So by the way, like this is the first of many examples of what are called orthogonal polynomials. There are like tons of different kinds of orthogonal polynomials, and they all tend to be like tailor-made to solve a particular differential equation. But this one here's the definition. P0 of x equals to 1, and Pn of x equals to 1 over 2 to the n times n factorial times the n-fold derivative with respect to x of the function x squared minus 1 to the power n for n equals to 1, 2, 3, dot, 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 dot. Now he says that these form an orthonormal system. These form orthonormal system for L to minus 1 to 1. For convenience, we write, oh, okay. He's going to make up a name for the x squared minus 1 polynomial. He's going to call that, yeah, he calls that little piece of n. I got to be careful. So these, I'll put some feet on these ones, big p's, right? And the little p, this thing here, little p sub n. All right. So let's see here. What's he do? Whoa. Whoa. What is that? He's dropping some knowledge on us here, I think. I feel like this. Look at this thing. Integral from minus 1 to 1 of the nth Legendre polynomial times x to the m dx. He claims that is equal to 1 over 2 to the n times n factorial, the integral from minus 1 to 1 of p, that's the little p, I believe. Yeah, little p. I really need a, fine, little p, and now that's the nth derivative. That parentheses sub n, that means nth derivative of that with respect to x times x upper m dx. All right, now he's going to go on to describe how to actually calculate these by recursion. And let's see here if he ever does he ever up and actually give us a list of them? No, he just proves that they're an orthonormal system. So he doesn't actually he never actually starts listing them here either. I mean, he gives you the first one, you know. I mean, I would enjoy spending the next half hour proving that these are an orthonormal system. I'm not sure that's a good use of our time. But let me look at it for just a second here. See if I can at least understand this one. Right. Yeah, I think that seems inevitable. I'll say like this one here. So you notice that well, let me just one more step here. So this is literally the integral from minus 1 to 1 of 1 over 2 to the n times n factorial times the n-fold derivative with respect to x of, you know, well, this is Pn of x, right? And then times x to the power m dx, right? And oh, duh. Okay, so that's all that is. All right, so okay, well that's why that's true. And we say to calculate this, he you can integrate this by parts. Yeah, I think that's true. So let's see here, to integrate this by
he's integrating the derivative term, the n through the piece sub n of x, and then differentiating the x with the
So basically you're doing integration by parts with this piece right here
yeah.
being your dv, and this is your u, and the constant stays out. So you get 1 over 2 to the n times n factorial parentheses.
Times it's negative eight.
So that would be, so if we integrate that once, we get, well, the u is x to the m, obviously, right? And then the v is the n minus 1th derivative of that, right? So that's the v. And minus the integral v du. So that would be Pn n minus 1 of x. And then the du would be m times x to the m minus 1 dx.
But that first part is evaluated from negative 1 to 1.
Oh, yes, thank you.
Yeah, and he's saying that the actually the UV part is 0 because the piece of it evaluated at 1 and negative 1 is going to be 0. The x squared minus 1.
Oh, pretty. Yeah, you can see that from the formula. So,
And so it just reduces to 1 over 2 to the n factorial times negative n.
so then you get minus m over 2 to the n times n factorial integral from minus 1 to 1 the n minus 1th derivative of the little p function times x to the m minus 1.
And they keep doing that user recurring formula or something.
So basically, dot, 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 you get minus 1 to the m times m factorial over 2 to the n factorial integral from minus 1 to 1 p n n minus n, I suppose, n minus m dx. Is that what we get?
He has. Oh, you keep the last interval in there. Yeah, I think. Well, for that last interval, I think there'd be one more.
Still an x left?
He has taking out the 2 to the n factorial term. He has final result is negative 1 to the n factorial times little piece of n to the n minus 1 derivative of x divided by 1. So I think it just takes that last.
So just,
I think it's next.
my counting's a little bit off there. I need that like that. There now I've got the counting right.
Apparently, yeah.
Okay.
Well, yeah, I guess also there's, I guess it'd be negative 1 to the n minus 1, then n minus 1. Oh, sorry, m. What was it? Yeah, n minus 1 factorial, because after you take the interval, it's going to be n.
Oh, that's only m minus 1 factorial?
I guess I'm just reading from based on the final result you're asking.
Where are we? Where are you looking at?
Right above line 3.13.
3.13?
With the n less than n. So repeating application of this operation ultimately leads to this. And so you have you kept the.
Oh, okay. I did the next to the last
Yeah,
step.
next to the last one.
Oh, okay.
Which is fine. It's fine. That's
Okay, so you're right. That would be m minus 1 factorial then.
yeah.
But then the point is, again,
Yeah, you just do it again.
those functions integrate to 0 because they, well, how to say that?
Yeah, at the end of it, you're still going to plug negative 1 to 1 back into a piece of it, little piece of it.
Right. So, but then this is 0. Okay, great. So what does that show you? What does that mean? What does that mean for this to be 0? That means, right, that the inner product, right, of the nth Legendre polynomial with what? With xm is equal to what? 0.
Or n less than
for m less than n. Let me see here.
Interesting.
So, listen, the way I have seen these before, like usually the way I discover Legendre polynomials is the following. Like here's how I typically see Legendre polynomials. My previous experience, all right? Previous experience of me. You start with the set 1x, x squared, x cubed, ... right? Let me call that t, right? And then you run what's called the Gram-Schmidt algorithm on this with respect to this notion of inner product. So in other words, you start by saying, I want, see, that's not even normalized right. Huh. What's the inner product? Does he ever come out and say it? What's the, or this is just a, this is just a bunch of calculus here. He hasn't told us any space or anything, has he? He's L2.
Well, later on he says to obtain an orthogonal system from.
Oh, he has to, he says the square root of n plus 1/2 times Pn. Eventually he confesses the square root of n plus 1/2 times Pn. These give orthonormal system. For L, what is it, L2 minus 1, 1? All right, so let's see how that works for 1. So like for 1, if you plug in 1 into that, I mean plug in 0 rather. So let me call the normalized one. I need to give it yet another name. I don't know, p hat. There we go, p0 hat, right? So allegedly that would be, 1 over the square root of 2, right? That makes sense, because then if we look at the inner product of p0 hat and p0 hat, what do we get? Integral from minus 1 to 1 of 1 over 2 dx, right? Which is 1. So you need the 1 over the square root of 2 to normalize it. Okay, so then the way you get to P1 then is P1 is the what you do is you define P1 to be equal to the projection, well I call it the orthogonal projection in the P0 direction of x. So what I do is I take the polynomial x and I subtract off the inner product of x with P0 in the P0 direction. So like, and this would be P1. This wouldn't be the P1. This would be, I shouldn't call this P1. It may not be his P1. I should call this something else, like P1 tilde there. Is that horrible enough? So then, what is this? Well, this is the integral, right? Integral from minus 1 to 1 of, x dx over square root of 2, which is what?
Is that x is 4?
Isn't that 0?
Oh.
I think this is 0. It's
Sorry, yeah, it's odd.
the integral of an odd function.
Yes, sorry.
So this is 0. So I'm alleging that P1,
Yeah, sorry.
you're fine. I'm alleging that P1 of x apparently is just equal to, well, if I believe his normalization, curses. Well, P1 tilde of x anyway is just equal to x. I'm not sure about the normalization yet. I can figure out the normalization, of course. What I'm wondering is, if you try this for P1, what do you get? Do we agree? What's his P1?
Yeah, that would be it.
So, yeah, we've got 1 over 2 to the 1 times 1 factorial, right? Times derivative with respect to x of x squared minus 1, which is x. All right, so, hey, we agree.
Are you doing the Graham-Schmidt process?
Yeah.
Okay.
So the Graham-Schmidt process, what it is you subtract off the pieces which could be parallel to the vectors up to the point that you've orthogonalized, right? So like the next thing in the Graham-Schmidt process would be the next thing in the Graham-Schmidt process would be I would take P2 tilde would be the I view it in terms of oh, you got it. Thanks, Audrey. P is orth of the orthogonal direction words. It's the orth of the orth of x squared.
There's the best of the best and the orth of the orth.
It's like you just keep removing the parts which are undesirable. So what I mean by this is, what this works out to is x squared minus the inner product of x squared with p1 hat in the p1 hat direction minus the inner product of x squared with p0 hat in the p0 hat direction. I subtract those two pieces off. That's how I get a P2 tilde, which will be orthogonal. By construction, this will make P2 tilde orthogonal to P0 and P1. This is the Graham-Schmidt process. And, you know, whatever that works out to, apparently this is what? X squared with x, right? Which is the integral from -1 to 1 of x cubed, which is 0. And the other one maybe is interesting, x squared with P0. P0 was 1 over root 2, right? So that's the integral of x squared over root 2 from -1 to 1, which is, you know, x cubed over 3 root 2 -1 to 1. I think that's just 2 over 3 root 2, right? So if we go through all this rigmarole, we've got x squared minus, as it turns out, 2 over 3 root 2 P0, but P0 was just 1 over the square root of 2. So my P2 tilde would be x squared minus 1/3, I think. Now I'd be interested to see if his P2 is the same as my P2. I want to see if my P2 tilde is the same as his P2. I'm kind of curious. What's his P2? 1 over 4 times what?
The second derivative of x squared minus 1 to that squared.
ddx of x squared minus 1.
Squared.
x minus 1, oh, squared.
Squared minus 1 squared.
Oh,
Yeah.
squared. Okay, gotta be careful here. So that's 1 over, that looks like an 8, right? ddx of 2 times x squared minus 1, yeah, times 2x, very good, which is 1/8 of 2 times 2x times 2x plus 2 times x squared minus 1 times 2, which is, that gives us 8 plus 4, 12 over 8. 12 over 8 is also known as, I think I get 3 halves. I think I get 3 halves x squared minus what? Minus 1/2, right?
Yeah.
So this is equal to 3 times my, well, this is 3 halves times my x squared minus 1/3, right? So they're not the same. They don't match up. The Legendre polynomials that are generated through this generating function, dark magic, that he begins the example with, they're not the same exact polynomials that will generate through just the straightforward, well, straightforward is maybe the wrong turn of phrase, but the application of Gram-Schmidt on the monomial basis. This guy's here, this is the monomial basis.
This would be different because that's orthogonal, or the orthogonal system, minor Gram-Schmidt process, but that's the original design that we were looking at.
Yeah.
Now we have to multiply by the square root of it plus a half.
So let me try to like take a step back here and describe what's going on with some words rather than equations, because words are easier. So I think so what this result is saying is that the nth Legendre polynomial will be perpendicular, right? It's perpendicular to 1 to x squared, all the way out to x to the n minus 1, right? This is perpendicular to the nth Legendre polynomial, right? So that makes sense. But like that's, so if you construct the nth Legendre polynomial by taking x to the n and removing the pieces, right? Basically removing the pieces which are parallel to these, it achieves the same. But it's a little bit more complicated than that, because the way Gram-Schmidt goes is you don't keep removing pieces that are in these directions. You remove the pieces which are in the massaged orthogonalized base. Like you take these and you're orthogonalizing them as you go, and it's those that you're subtracting the shadows of the orthogonal pieces off the x to the n. Anyway, these are two different ways to come at the same thing. The ultimate goal is to create a orthonormal basis for this L2. And it's not clear to me why it's a basis though. I mean, that's too much. It's an orthonormal system, right? I don't know if it's a basis or not. It's definitely an orthonormal system. I mean, this is not an orthonormal system, because if we integrate, if we integrate like, yeah, like x and x cubed, you integrate that the inner product of that gives you an integral of x to the fourth, which is non-zero, right? Those are not perpendicular. So if if you, I mean, if the sum of the degrees are odd, those are perpendicular, right? With respect to this inner product, like if we take the inner product of, say, like x and x squared, those would be perpendicular because we have integral of x cubed from -1 to 1, which is 0.
Yeah.
So it's an interesting kind of problem. Like, these are pairwise perpendicular. Like any two, if you think about the monomial basis, right? The monomial basis is such that any two subsequent ones are perpendicular, which is kind of cool. And yet, if you go two, if you look at, not nearest neighbor, but the next nearest neighbor, then they're not, if you go 2 over like 1 with x squared, those aren't perpendicular because the integral of x squared is non-zero. And likewise, x and x cubed are not perpendicular. It's I don't know. So, but anyway, I think I've said entirely too much about this example. Anyway, he does have a proof, right, that that these form an orthonormal system. Although he actually hasn't really kind of told you what they are, has he? Oh well, sorry, I haven't shown you more details here. All right, let me kind of move on here. I want to get to some of the theory, not just these examples. So these are Legendre polynomials. So the next one is the Hermite polynomial. Come on, marker. Hermite polynomial. And this one, he defines it hn of x is equal to -1 to the n times e to the x squared. Well, that's not a polynomial. Times, well, maybe it is. Oh, look at this. The nth derivative of e to the minus x squared. Oh, I take it back. That is a polynomial. All right. Yeah, so if you think about the differentiation, it's going to produce exponentials of the minus x squared everywhere, right? So it will be a polynomial after you go through the calculation there. Sorry, the Legendre thing's bothering me. If I had more time and I had a list of like the first 10 to show you, I'd feel better about my day, you know? But it's okay. So here, he says if you let phi n of x equal to e to the minus x squared over 2 hn of x, then he says these form an orthogonal system in L2R. All right, so let's look at the calculation here. We might be able to understand this one, I guess. You got phi n, phi m, and so what you're going to get is, all right, yeah, -1 to the n plus m, right? Integral from minus infinity to infinity of e to the x squared times the nth derivative of e to the minus x squared times the mth derivative of e to the minus x squared dx. So what he says is that if you repeatedly apply integration by parts, right, you can see that for n not equal to n. Oh, am I gone?
Yeah.
Sorry, Audrey. There you go. So if we repeatedly integrate by parts here, if you think about what's going to happen, let me not even write it out. Let me just describe what happens. If we integrate by parts, what it does, of course, is it removes the derivatives, right? And it produces terms that are proportional to, you know, e to the minus x squared, right? And so you're going to have basically terms outside which get evaluated from minus infinity to infinity in the sense of course, the limiting process, right? But the thing is, as you do the integration by parts, you're ending up evaluating from minus infinity to infinity these functions, which then are 0. So basically, through repeated integration by parts, which, you know, if I had more time and energy, I would try to do, but I'll just say that this gives us 0. And you can kind of see that essentially the heart of the matter being eventually you get to stuff like this.
Isn't that the Gauss? Oh,
But yeah, this is the Gaussian. That's true.
where that not be zero? Oh, it's
Yeah, it's not. Well, exactly. It's not just the Gaussian. It's something else. I mean, there's also this e to the x squared out here, which is blowing up, right? But not really, because there's always at least 2 of these to work against it to actually make it smaller. So, and then so okay, so that proves that it's a orthogonal system, and then you got to normalize the thing. So how do you normalize this thing? To normalize it, what you have to do is you have to calculate the inner product of phi n with phi n, right? So if you calculate the inner product of phi n with phi n, that means you're up against the integral of, you know, well, you get minus 1 to the 2n, which is just 1. So it just integral from minus infinity to infinity of, you know, e to the x squared times the nth derivative of e to the minus x squared, right? And you have 2 of those. So I guess I could write it, I could square it if I wanted to, right? I mean, that's what you're integrating. And then the question is, how do you integrate such a thing? Right? So this is, oh, so he does a sneaky trick. He pulls, huh.
Someone's pretty crabby.
Uh-oh, well, thank you for visiting. Have a good rest of your afternoon.
Way more than I thought.
I feel that way every day in here. So he does something sneaky here. Oh. So, but he does an algebra trick before he does that, though. See, because he brings a. I think he puts. If you put an e to the minus x squared in here, what's the cost of that?